Okay, this is section 5.2, Logarithmic Functions, Part 2. We have here three new properties of logarithms. Okay, we're going to use these a lot when solving equations involving exponentials and logarithms. The first is called the exponent property. And the way I like to remember this is the idea is that it allows us to take whenever we have a logarithmic expression with or of an exponential, what we can do is pop the exponent out in front as a multiplier or multiple. So log base b of a to the r becomes r times log base b of a. And actually this is just a consequence of property number 2 here, the sum property. I'll show you why in just a minute. What is the sum property though? Well, remember that if we have e to the, well, let's do this rather. Let's do, if I have base b raised to the a power times base b raised to the c power, this is equal to b to the a plus c power. So that's a property of exponentials. And since the logarithm is the inverse of exponentiation, you would expect this to do the reverse, and that's exactly what happens. So here we have the product of two exponentials is equal to the exponential of the sum. Okay? Well, with logarithms, what does it become? It becomes the sum of two logarithms is equal to the logarithm of the product. Okay. Also recall that if we have, say, b to the a power divided by b to the c power, this is equal to b to the a power minus c. Okay, well, in logarithm land, the equivalent idea is expressed as the difference of logarithms is equal to the log of the quotient. Over in exponential land, we have the quotient of exponentials is equal to the exponential of their difference, right? So in logarithm land, it has to be the inverse. Okay, so we'll often use these properties of logarithms to rewrite several log expressions being added or subtracted into a single logarithmic expression, because this is going to allow us to solve equations more easily. But be aware that sometimes you want to do the reverse. Sometimes you do want to go the other direction. So you can use these properties either way to break apart the logarithm of a complex expression into the sum of simpler logarithms. Sometimes you want to do that. Okay, but typically we're going to go in the forward direction, like this first exercise. In this first exercise, we're asked to write the following as a single logarithm. So we have the expression 5 times the log base 8 of x plus 3 times the log base 8 of x. So what we can do is use the exponent property twice. We'll use that twice to rewrite this as log base 8. Let me turn that off. Base 8 of x. Oh, sorry, I forgot to put the multiplier 5 up as an exponent, so that becomes x to the 5th plus log base 8 of x cubed. Okay, so I'm using the exponent property there in reverse. Okay, notice this is one of the times I want to use it in reverse. And now I'm going to use the sum property. I have the sum of two logarithms. I can write this as a single logarithm of the product. So this is equal to log base 8 of x to the 5th times x cubed, Or, of course, this is just log base 8 of x to the 8th power. Okay. Let's see another example. In this exercise, again, we're asked to write the following as a single logarithm, but we have a difference of logs here. The difference of two logs can be rewritten as the logarithm of their quotients, So we get log base 4 of 12x to the 8th power over 3x cubed. And that expression inside, of course, can be simplified. We would probably simplify that to log base 4 of 12 divided by 3 is 4, and 8 minus 3 is 5. So we would get 4 times x to the 5th power. Okay, moving along. Write the following as the sum or difference of logarithms with exponents as coefficients. Okay. I think I'll just think of it as a quotient first. And so I'll use the difference property first. And let's rewrite this as the log of the numerator expression, which is x to the 16th times y to the 11th minus the log of z to the 6th power. Okay, but I'm not done yet, because I have the logarithm of a product, so I can rewrite that as the sum of logs. So I'm going to expand that as log of x to the 16th plus log of y to the 11th minus log of z to the 6th power. Okay, and the prompt does tell us to write the following as the sum or difference of logarithms with exponents as coefficients. So we can further decompose this, so to speak, into 16 times log of x plus, if I pop the exponent 11 out front as a multiplier, I get 11 times log of y minus 6 times log of z. There we go. That's as simple as we can get that, or as decomposed as we can make that. Okay, now let's start solving some equations involving exponentials. So whenever you see an equation where the variable you want to solve for is in an exponent, you're going to need to use a logarithm. And I'm going to show us two different ways to solve this equation. The first would be to use the idea of one of the first properties we saw, which was what? It was, I'll write it out over here. If we have log base b of b to the x, this is just x. Okay? So the point is, if I take the logarithm base 5 of both sides of this equation, well, then the left-hand side will just become x, right? In other words, log base 5 of 5 to the x, well, that's just x. But I got to do the same thing to both sides of the equation, of course. So I have log base 5 of 23 on the right-hand side of the equation. So the left simplifies to just x, and there we go. We get log base 5 of 23. Okay? Now, at this point, if we needed to actually, we'd probably want to compute a value, and what would we do? We would then apply the change of base formula and rewrite log base 5 of 23 as maybe the natural log of 23 over the natural log of 5, right? So there we go. Okay. So there we go. There's the answer. We could plug that into any scientific calculator and compute a value. I'm not really, most of the time when solving an equation, I don't really care that you compute a value, although it is a good idea to compute the value and then check. Plug it back into the original equation and check to see, does it actually satisfy the equation, right? There's another way to approach this, though, that's a little bit faster, okay? And this goes along with the idea I previously mentioned that the base of exponentiation or the base of your logarithm is kind of irrelevant. It doesn't matter which base you choose. Just do whatever convenient for you. And it turns out, notice, if I just apply the natural logarithm function to both sides of the original equation, in other words, I take the natural log of 5 to the x power and set that equal to the natural log of 23. Okay. Well, I haven't solved for x, have I? My x is still in the exponent, but now that it's wrapped inside of a logarithm expression, I can use the property, the exponent property of logarithms, and I can pop that exponent x out in front of the logarithm as a multiplier. In other words, this left-hand side becomes x times the natural log of just the base, which is 5. Okay, and then now to solve for x, I just divide both sides of the equation by the natural log of 5, and I get x is equal to the natural log of 23 divided by the natural log of 5, which is what we got by applying the change of base formula. Okay, so point is that the choice of base is not important. It's the best advice I can give is just use the base that's most convenient for you. Okay. Let's try the next exercise here. Solve the equation for x. We have 2 to the x equals 10. I can't express 10 as a power of 2, so I can't solve it the easy way. But I can just take the natural log of both sides of this equation and then, of course, I'll use the exponent property on the left-hand side, and I get x times the natural log of 2 equals the natural log of 10, and thus x is equal to the natural log of 10 divided by the natural log of 2. Okay, and what do I mean by checking our work? Well, I mean this. Let's punch this into the calculator. We want to take the ln of 10 and divide that by the ln of 2. We get about 3.3219. So let's check. Does that solve our equation? So 2 raised to that power is, yep, indeed, it is 10. Okay, so you can always check your work that way. Moving along, solve the equation for x. Okay, I'm going to use one of the first properties of logarithms we used and just take a natural log of both sides. And I have the natural log of e to the 3x is equal to the natural log of 25. And recall that whenever you have a natural log of an exponential base e, well, that's equivalent to just whatever the exponent is. And in this case, it's 3x. So the left-hand side simplifies to 3x. And thus x is equal to the natural log of 25 divided by 3. Okay, let's just check our work again. Natural log of 25 divided by 3. I get about 1.073. So let's check our work. The e to the x button on my calculator, I have to use the second. And ln button. Okay, and I want to do 3 times this value. Enter. And I get 24.999. Yeah, so I get 25 within the rounding error. Good. Okay. Let's see, we have a word problem here. Let's expand this. The value in millions of dollars of exercise treadmills bought from China can be approximated by the function f of x is equal to 0.8208 times e to the 0.0927x, where x equals 0 corresponds to the year 2000. In what year did or will the exports reach 5.4 million? Okay. I think the first thing to check is to verify that this function is already using units of millions of dollars. And indeed, yes, the function f of x is measuring the value of exercise treadmills in millions of dollars. So what we want to do is set the function equal to 5.4 million and solve for x. This is what we want to do. Okay. I'm going to show you, though, a little technique that I really like to do that I think is a huge time saver. Okay? And that is, I'm going to rewrite f of x as just a times e to the rx. Okay, where a is that 0.8208 and r is that 0.0927 value. Okay, no one wants to write those decimal values over and over again when solving an equation, so don't. Okay, what we're going to do is we're going to just remember that a and r are constants. E is also a constant, and we want to solve for x. So the first thing I'm going to do is I'm going to, let me write down, of course, what I mean. Of course, a is equal to 0.8208. I don't want to forget what these values are for. And r is equal to this 0.0927. Okay. But to solve this equation now, I want to isolate that exponential expression, so I'm going to divide both sides of the equation by a. And I get 5.4 over a is equal to e to the rx. Okay? And I don't have to write all those decimal digits. Super frustrating. Now I want to get that expression r times x out of the exponent, so I have to take a logarithm. And since I have exponentiation base e, it makes sense to use the natural logarithm here. So we'll take the natural log of both sides. I have the natural log of 5.4 over a, and of course the natural log of e to the rx power is just r times x. So then x is going to equal the natural log of 5.4 over, 5.4 over a, all divided by r. Okay, so now finally I'm going to plug in the values for a and r. So x is going to equal the natural log of 5.4 over a, which is 0.8208, divided by r, which is 0.0927. Okay, and this is the expression I want to evaluate on my calculator. So let's do that. Let me expand the screen a little bit here so you guys can see better. The natural log of 5.4 divided by 0.8208, close paren, divided by 0.0927. Okay. And we get about, we'll say 20.32 years. Was it? Yeah. Okay. Of course, where x equals 0 corresponds to the year 2000. So what this means is that the actual time when we expect the exports to reach 5.4 million will be 2000 plus that x value, or about the year 2020. So I'll put an approximately equal here. So early on in the year, fairly early on in the year 2020 is when we would expect these to reach 5.4 million. So just recently. Okay, so let's check our work by plugging it into the function and seeing if we plug, and now we need to plug this value, the x value, back into f of x to check our work. So let's do that. So we want to compute 0.8208 times e to the r, which is 0.0927, times the value I just computed, which is up here. Copy that in, get out of the exponent, and enter. There we go. We get exactly 5.4. So, yep, this checks out, and thus we would expect the exports to reach 5.4 million in the year 2020. Okay, so why not just use the digits? You're welcome to do it that way if you want. You could write out all the decimal numbers, but I think this is superior. Why? Well, for one reason, I just did this problem and I left out one of the digits in the decimal numbers and I got the incorrect answer. Now I was able to realize that I had the incorrect answer because I checked my work. But when I redo it with just using the symbols, then I think it makes your computations a lot simpler. What happened earlier was that when I wrote down, was rewriting one of the decimal values, I just left out a digit or added a digit. I don't remember exactly what happened now, but The point is, though, is that writing all those decimal values over and over and over again, it's easy to make a mistake. Introduce a digit, change a digit, something like that. So if you just use simple symbols like I did here, like A and R, it's far harder to make such a mistake because you just put the decimal values in at the very end. And it's a time saver too. Okay. Let's try the next exercise. The value of a car is depreciating according to the model V is equal to 18,000 times 0.85 t, where V is the value of the car t years after it was purchased. When will the value of the car reach 15,000? All right. So we just want to set V equal to 15,000 and solve for t. Okay. Should I use symbols here? We could. These are pretty simple numbers, though. I think I'll just use the numbers because we're going to get cancellation immediately anyway. So let's see here. What we want to solve is 15,000 is equal to 18,000 times 0.85 raised to the t power. Okay, divide both sides of the equation by 18,000. I get 15,000 over 18,000. And of course, that 1,000 cancels with that 1,000. And the right-hand side is just 0.85 raised to the t power. Okay, 15/18. That simplifies down to both are divisible by 3, so I get 5/6. Yeah, so these are fairly simple numbers. It's not a huge advantage to use symbols instead. Okay, let's see. I think I'll take the natural log of both sides. I could take logarithm base 0.85, but no need. Natural logarithm will work just fine. I get the natural log of 5/6 is equal to, and remember, the natural log of an exponential is equal to what? This is equal to t times the natural log of just the base, 0.85 in this case. So we get, if I solve for t now, I get t is equal to the natural log of 5/6 divided by the natural log of 0.85. And let's compute a value for that on the calculator. Let's see here, clear. The natural log of 5/6 divided by the natural log of 0.85. Is that correct? Yes. It's about 1.12. Okay. Yeah, that seems right. Basically, the car loses 15% of its value every year. 15% of its current value every year. So 15% of 18,000 is what? 0.15 times 18,000. 2,700, so we do 18,000 minus 2,700. It's 15,300. Yeah, so it's going to take just a little bit more than 1 year to lose to go down to 15,000. So this seems like a legitimate answer to me. So 1.12 years. Okay. How long will it take an investment of $13,000 to double if it is invested at 6% compounded monthly? So we want to use the compound interest formula, which is, let's recall that, the account balance as a function of time, A of t, is equal to A times, which is the principal, times 1 plus the percentage rate divided by the number of compounding periods per year raised to the k times t, the number of compoundings in total. Okay. And what we want is we want to know how long is it going to take for 13,000 to become 26,000 to double. So we want to solve this. Again, I don't think it's really necessary to use symbols here because we're going to get some really nice cancellation. Let's see, remember we got to write the 6% as a decimal. And we're doing monthly compounding, so k is 12. And we don't know the time, so we're going to do, but k is 12, so we have 12t in the exponent. Okay. I'm going to do a simple little calculation here and determine what is 0.06 over 12. 0.06 divided by 12 is 0.005. Okay. So that expression in parentheses is equal to 1.005. So to solve the equation, I'm going to divide both sides by 13,000. And of course, that's just 2. And this will equal 1.005 raised to the 12t power. Okay. Now I want to take the natural log of both sides. So I get the natural log of 2 equals the natural log of 1.005 raised to the 12t power. But remember, I can use the exponent property of logarithms to rewrite this as 12t times the natural log of the base 1.005. Okay, solving for t, let's see, I'm going to have 12t is equal to the natural log of 2 divided by the natural log of the base 1.005. And now I'm kind of wishing I had used a symbol for the base, maybe just b or something. Lastly, we divide both sides by 12, and we get the equation t equals the natural log of 2 divided by 12 times the natural log of 1.005. And let's use the calculator to compute a value for this. Let's see. Natural log of 2 divided by, let's put this in parentheses, 12 times the natural log of 1.005. And close out all those parentheses. Enter. So we get about 11.6 years. We always measure time in years in financial calculations. Okay. So at 6% interest compounded monthly, it will take your money 11.6 years to double. Okay. Here's an interesting thing too. Notice that this is A right here. A is 13,000, but what is this value over here? It's just 2A. So we're always going to, no matter what you put into the account initially, it's kind of irrelevant. It always cancels out of the equation that you eventually need to solve. Notice this expression here does not involve the principal of the account. Nowhere do you see the number 13,000 in that expression. It's irrelevant. The only thing that determines the doubling time for the investment account is the interest rate and the compounding, how frequently you compound. Okay? So, let's move on. Solve the following equation for x. Log of x plus 3 equals 1. So we want to gather those logarithms. Let's use the sum property of the logarithm to rewrite the left-hand side. Let's see, we don't need the calculator anymore for this. So let's rewrite the left-hand side as, instead of the sum of two logarithms, we'll write it as a single log of a product. In fact, we'll write it as the log of x times x plus 3. This equals 1. Let's see. Now I want to get those x's outside of the log function. So how do I undo log? And what base of logarithm is this? This is a common logarithm, so it's base 10. So how do I undo logarithm base 10? Exponentiation base 10. In other words, I want to exponentiate both sides of the equation by 10. So I'm going to get this expression, 10 to the log of, what is this? I'll write this as x squared plus 3x. And I need to exponentiate the other side of the equation as well, base 10. Of course, 10 to the 1 is just 10. And the key idea now is that logarithm base 10 and exponentiation base 10 undo each other. They're inverses. So the left-hand side simplifies to x squared plus 3x equals 10. And now I have a polynomial equation. We know how to solve those. We use the power of 0. We get x squared plus 3x minus 10 equals 0. And we factor, if possible, we can factor this. Let's see, we're going to get 2 and 5, right? And I want this one to be positive and the other one to be negative. Does that check out? Let's see. Negative 2 times 5 is negative 10. Negative 2x plus 5x is positive 3x. That checks out. So we get x is equal to 2 or negative 5. There we go. And we're all done. No. And this is an important thing about solving logarithmic equations. Sometimes we get what we call extraneous solutions. Notice if I take this solution, x equals negative 5, and plug it back into the original equation, well, I'm going to have log of negative 5, won't I? That's undefined. Okay, that's going to give us a complex value, and we don't want complex values. It doesn't make sense in the context of our problem to consider complex values. So we call that, it is a solution. It does actually solve the equation, but it's extraneous because in the context of our problem, complex numbers don't make sense. Sometimes they do, not here. So we call this an extraneous solution, and we often just cross it out. And how do you spell extraneous? It's spelled like this. Extraneous. Okay, so there we go. Notice if x equals 2, if I plug it into both logarithm expressions in the original equation, it's completely fine. I get values that are in the domain of logarithm. So next, solve the following equation for x. We have log of x plus 5 minus log of x plus 3 equals 1. Again, I can use a property of the logarithms to combine those two logs into a single log. And I'm going to use the difference property of logarithms, which says that the difference of logs is equal to the log of the quotient. In other words, this left-hand side will simplify to the log of x plus 5 divided by x plus 3. Okay, now I have my x values inside of a logarithm function, a single logarithm now. I can undo log base 10 by exponentiating base 10 again. And I'm not going to write out the whole equation. I'm just going to remember when I exponentiate this left-hand side by base 10, I'm just going to get the argument to the log function. I get x plus 5 over x plus 3. Now I have to remember to exponentiate base 10 on both sides. 10 to the 1, this is just 10. Okay. Now I have a rational equation. I can solve this by what? By multiplying both sides by x plus 3. So I get x plus 5 equals 10 times x plus 3 in parentheses. So x plus 5 equals 10x plus 30. Let's see, if I subtract x from both sides, I get 5 equals 9x plus 30. And then if I, well, let's see here. If I subtract 30 from both sides of this equation, I'm going to get negative 25 equals 9x. So x is equal to negative 25 ninths, which is, what is that? Negative 25 divided by 9. It's about negative 2.7 repeating. Okay. So we got one solution. And let's see. Is this an extraneous solution? Can we put negative 2.7 repeating into both of these logarithm expressions, and then will the resulting value be greater than 0, or positive? And in both cases it will be. So this is, even though it's a negative number, it is a valid solution. It's not extraneous. Okay, so we can go ahead and box that. Okay, and this concludes section 5.2 on logarithmic functions, part 2.